I'm very happy today to welcome everybody to today's event, which is International Minds in Finland. And today's event is very special because our guest is Lars Scott, a fantastic scientist who has been studying all his life very important physical problems. And I would like to thank also the library of this place, which is very nice place that creates some calm atmosphere, which is very kind. So thank you for this. And Lari, I think that this subject is very challenging. So the most important problem in this kind of matter that describes the problems of our universe and problems of physics in the 20th century is probably to make it understandable for people who don't understand physics, who don't study it a lot. Because physics naturally has advanced so much in the future, so it is very difficult to explain its problems in a natural language. So I guess this kind of challenge is up to Lari Scott today. So please, I welcome Lari to make a lecture about what has been wrong in physics in the 20th century. So thank you, please.
Thank you. I had originally planned to acquaint the audience with certain elementary ideas of mathematics which are evident in every weather map. However, I decided that due to the length of the material that it might be too much to sit through it all, but perhaps I should just briefly mention a few basic ideas that are essential. When you look at a weather map, you'll notice that there's usually a low pressure zone and a high pressure zone, and what happens to the gas between the high pressure zone and the low pressure zone? Well, we know that there is a wind which will blow in that direction because this is low pressure. This type of thing is called a gradient, and when the lines are very close together, it's much like a topography map of a mountain. When the mountain is steepest, the gradient is steep or higher also. And so we have a term in physics which you'll be seeing in this presentation. And the gradient of the pressure is a direction perpendicular to the lines of constant pressure, and it goes, as I say, perpendicular to these isobars or constant pressure lines. So as you look at a weather map, you will realize that these processes are working there. But there's another thing that happens. If you've ever seen a tornado where the rotation of air is very strong and it comes down like this. We have another symbol in physics called the curl. It's usually the curl of some vector. And we're not talking about the curler of someone's hair. We're talking about a mathematical construct that allows us to understand how this rotation is measured and how it can affect the physics of the situation. And sometimes in these cases, you will find that air is blowing around usually a low pressure. So you have a swirling effect that happens. So whenever you see this thing gradient, it's usually a gradient of a scalar, that is not a vector, not a quantity with both magnitude and direction, but only this is only a function, that is not a vector. Whenever you see these terms in the mathematics that I sometimes will show you, I don't want you to become flustered and daunted by the presence of these symbols. I will also be presenting things that show elementary tensor analysis. Here again, I don't want you to become so frightened by the appearance of the mathematics that it makes you reel from it. It's all very logical. It's all actually very simple. It just takes a little experience to be able to understand it. So with that, I will proceed with this presentation. You know, when we say that there are things that went wrong with 20th century physics, there's also a great deal that went right. And so before introducing this topic, what went wrong, I'd like to tell a little bit about the people who created 20th century physics. And there's certainly a great deal that went right during the 20th century. I don't want to give you the impression that we were fed a crock of malarkey or a bad load of information in 20th century physics. That's not true. So it's very appropriate that we give credit to and admire and appreciate these great figures of the last century. The following list is not complete, but I think that we should mention these people, many of them. I may not have time to go through all of them. But Max Planck postulated the existence of light packets, resolving the problems with black body radiation and thermodynamics. He was a great physicist. A great many of these people are Germans, but there are others. I will be presenting people from several different nationalities who played a role in this. Einstein made, of course, major breakthroughs. He got the Nobel Prize in quantum theory, even though some of his greatest contributions were special relativity and general relativity, that is, theory of gravitation and cosmology. Lorentz, we've heard a little bit before about these transformations that are used in relativity. Another figure that I want to point out is Henry Poincaré, who established the importance of groups in relativity, proved that the electron is unstable. Back in 1906, Henry Poincaré knew that the electron, as our physics understanding currently limits us, the electron is unstable according to current theory, which means it should blow apart, and yet it doesn't. I'll be discussing that problem shortly. Niels Bohr is the father of modern atomic theory. He debated Einstein successfully. Einstein and Bohr got in an argument once, and Bohr won. So Einstein wasn't undefeated when it came to physics or understanding of physics, even though we tend to think that he was a great genius, but he had his limitations. Bohr also clashed once with Erwin Schrödinger. if I can pronounce his name correctly. There are other great figures. Schrödinger, whose equation allows us to measure or to predict the spectrum of elements and compounds and molecules. Heisenberg, who developed a famous uncertainty principle, and he discovered that you cannot measure the exact motion and the exact position of a particle with unlimited precision. It's either one or the other, but there is a relation called his uncertainty principle, which limits the precision by which you can measure both momentum and position of a particle. Paul Dirac created the most accurate ever relativistic wave equation for matter with spin. So he discovered that in order to understand matter more perfectly, you have to include the fact that many of these particles have a intrinsic spin. It is as though they were rotating, although that is not quite an accurate representation of it. Louis de Broglie, he first presented the thesis, and they were going to throw his thesis out, but Einstein said, wait a minute, I think that de Broglie has a good idea here. And so he presented his ideas that matter and light possess properties of both waves and particles. There are others here. Hilbert discovered the math to solve many of these difficult problems. Pauli understood the role of spin in quantum mechanics, quantum theory, atomic physics. Max Born said, I believe that probability plays a role in physical processes, and so the quantum theory became a theory of probability, or probability became a fundamental part of modern understanding. Minkowski taught Einstein tensor calculus. When he first taught him tensor calculus, Einstein said, that's superfluous learnedness. I don't need that. But later on, Einstein realized that Minkowski's tensor analysis was very, very valuable, and with it, he developed his skills at tensor analysis to develop new theories of gravitation, and so it was a very valuable thing, even though initially he said, Das ist zuverlässige Gelehrsamkeit. That's superfluous learnedness. And he was wrong. He later realized how valuable it was. Schwarzschild, here's a captain in the German army on the Russian front who ended up discovering a marvelous equation, or a solution to a marvelous equation, which allows us to understand black holes. We will talk a little bit about it. And these black holes are found in nearly every galaxy. Leif Landau has discovered important things about superconductivity, where you lower the temperature of a substance and suddenly there's no electrical resistance in it anymore, and electrons go round and round and round forever, and they never stop in superconducting substances. Eddington popularized gravitation theory in the English-speaking world. Emily Noether was the greatest woman mathematician of the 20th century, and her far-reaching symmetry principles are widely used today. You've heard of Marie Curie, Madame Curie. She's the only person I know of that got 2 Nobel Prizes, one in chemistry and one in physics. She discovered radium and polonium and used X-rays to X-ray patients and so forth. Rutherford discovered the nucleus. Arthur Compton discovered how photons scatter from electrons. And the list goes on and on. I mean, we have Enrico Fermi, Ernest Lawrence, Arnold Sommerfeld. Hans Bethe was a character. He, on the train, he solved a very difficult problem on the back, on an envelope or a tissue paper, I forget which was he was noted for his skill in solving very difficult problems, and he did this very casually while traveling from, I think it was traveling on the train to New York to explain something that had stumped many people. Edwin Hubble was an astronomer who realized that those nebulae, those clouds that he was seeing in the telescope, were actually other galaxies. And he began measuring them and found out that the distant galaxies were receding away from us, some of them at very great speeds. We'll talk a little bit more about him. Richard Feynman was one of the persons who formed the union of relativity and quantum theory. It's called quantum electrodynamics, or QED. And he made his famous diagrams called Feynman diagrams. I'll show you an example one later on. John Wheeler, father of the atomic bomb and numerous other things. Murray Gell-Mann, a great elementary particle physicist who predicted the existence of quarks. I won't go into them too much in this lecture. Stephen Hawking, for his knowledge of time and black holes and the Big Bang. Then there was Sheldon Glashow, the brilliant critic of string theory. Then another person important in quantum electrodynamics was Julian Schwinger, a protagonist of Feynman. There was an Irish physicist by the name of John Bell who discovered that quantum mechanics and special relativity are conflicted, that relativity and quantum mechanics don't agree very well, and he proved some results that were very profound. He's the only person that ever questioned relativity and survived professionally in doing so. Weinberg is one of the greatest living theoretical physicists today, unifying various complicated forces that are known to exist. And I'm sorry, there are numerous other persons whom we should mention, but we see that physics is very far from a wondrous pillar of uncontested logic and a bulwark of science that cannot be questioned. These people had many disputations, controversies, paradoxes, and enigmas, and we'll try to discuss a few of them. I hope that as we discuss the critique of modern physics of the 20th century, that you don't think that any of these people are to be blamed or deprecated in any way. I believe they're all great people. Okay, let's start with some of the main paradoxes of the 20th century. In spite of these outstanding achievements, there are a lot of hardcore issues of modern physics that have steadfastly resisted solution. One of the objectives we're going to talk about is to delve into some of these paradoxes and suggest possible solutions to problems that have perplexed the physics community. And I don't purport to have solved these issues conclusively, but only to cast some light on them. Physics has a lot of hang-ups. We have people who are afraid of offending the orthodox authorities. And we have preeminent figures such as Einstein and Dirac and many others whose achievements are truly outstanding. But scientists, because of the success of a few, scientists often cling to these old patterns of thought and are perhaps a little too afraid to strike out on their own and develop something different from what the authorities are saying, you know. So we have these roadblocks to further progress. We have a thing called peer review, and when you submit a paper for publication in many subjects, not only physics, it requires a group of people expert in that subject to review your paper and decide whether it's worth publishing. Well, unfortunately, if you have an idea that is brilliant, but your peer review person is well funded and doesn't agree with your idea, if he has a lot of money, maybe he's well funded by the National Science Foundation or some other group, and he may totally stop your publication. This is a bad thing because oftentimes it happens. We have people who attack the credentials of a person and not the ideas that he is presenting. And I find that's quite common, where if someone disagrees with the ideas, they don't attack the ideas. All too often they attack the person and say, oh, he went to a second-rate graduate school, or he got his degree from this place, which is nothing. And they attack the credentials, not the ideas. That's another problem. We have a slavish commitment to firmly held ideas often that happens. Ridicule of bold new discoveries, for example, cold fusion. When Pons and Fleischmann discovered cold fusion in the early 90s, the people who were well funded again, these guys who were high rollers getting money on hot fusion and tokamak plasma fusion devices, such as are prevalent and still have the majority of the money, they said, no, cold fusion is impossible, it can't be real, and so on. But we now know it is very real. And there are companies now poised to make a great deal of money with cold fusion. Most people don't believe it's possible, but it seems to be a remarkable new way of generating energy. We have people who have a dismissive, a pretentious, authoritarian viewpoint, like it has to agree with Einstein's opinion regarding causality, or it has to conserve energy as we know and understand it. We have a lot of things like this where people will dismiss something based on a strongly held idea that may or may not be right. Oftentimes people ignore strange and disturbing experimental facts. An example of that is a man by the name of Robert Nussbauer, who in 1957, he had not gotten his doctorate degree yet, and he realized, oh, I've discovered something remarkable here in the lab, but until I get my PhD degree, I better keep silent about it. So he waited till he got his doctorate degree before he published the Nussbauer effect. And this happens quite often, where people fear that what they are presenting is too revolutionary or will be rejected out of hand unless they have that all-important doctorate degree. Well, we have another roadblock, and that's the revolutionary nature of scientific discovery itself. For example, it took over 15 years before quantum theory began to be accepted, after Einstein initially published the paper in about 1905, I believe. Well, here's an outline of some of the things that I want to cover a little bit, and I know this is going to be a challenge for everyone, but these are the ideas of the 20th century that I believe, these are some of them, that I believe have suffered from some significant problems. One is the nature of antimatter. Second is cosmology and the expanding universe. We mentioned how certain scientists have seen that as they look out at distant galaxies, they find that the light from those galaxies is red-shifted, meaning the galaxy is receding at a very high speed, and the light coming from it is not the same spectrum as we would see if we were at rest with respect to that galaxy. So all of the lines are shifted so that the wavelengths of the lights are longer because the galaxy is moving away. We have this other problem I mentioned, the stability of the finite electron, and finally the wave-particle duality of light. This last problem is a mind-boggling problem because for over 100 years we've suffered with this problem that scientists have known, that particles and light seem to exist properties of both waves and particles. So let's begin with this talk about the areas of conflict in the 20th century. We have the quantum theory. Dirac promoted an idea for a sea of unobservable, virtual, negative mass particles. Well, it turns out that's a pretty tall order to swallow, as we'll talk about it later. But science also suffered from a number of other irritating problems as they tried to calculate, for example, the mass of certain things like the electron. And they're trying to calculate these properties from first principles. They noticed a lot of it blows up right in their face. They get infinity for the value of a mass of an electron. And of course, Feynman and Dirac, who developed this very technique themselves, they were the first to say, this is not right, don't believe it, there's got to be a better explanation. Throwing out infinities just because they're nonsense is not correct physics. We have to be able to know why we can ignore some quantity. We find that there's a lot of use of virtual, unobservable processes happening in physics. Sometimes these ideas are very fruitful. There are many things that go on that are not observed and that create a situation that is later observed. And so by postulating or believing that there's this period of unobserved activity, this is called a virtual process. They hope to understand nature better. Unfortunately, we find that in 20th century, the idea of virtual processes, in my humble opinion, has gotten out of hand. It's really grown into a monstrosity, if I may say. And we have, of course, the failure to account for wave-particle behavior. We have in relativity a lot of clashing between relativity and quantum theory. One of them, I once had the occasion to work with people who were trying to put a laser inside a very large airplane. And this laser light was supposed to be able to be very powerful infrared light and be able to shoot down objects using a weaponized laser on board this airplane. Well, we have a very remarkable process going on inside lasers. We have hundreds of trillions of atoms which are excited, and they're ready to decay down and emit a photon. And when they emit a photon, you don't know when they're going to emit the photon, but what we have noticed is that these really powerful chemical and gas dynamic lasers, the entire lasing cavity almost acts in lockstep, as though all of them are synced together. It's like soldiers marching across a bridge, all of them in lockstep. And if they march hard enough, stepping in unison, the force on the bridge can be quite bad and damage the bridge. Well, this same thing happens in lasers in a different scale, where hundreds of trillions of atoms which are excited are made to decay in unison, all in lockstep, in phase, what is called phase coherent, so that all of the waves line up from each emission of light from each excited atom. That is not easy to achieve, and yet with these high-powered lasers they were able to do this, and it calls into question ideas of local relativity, local causality, things that Einstein was fond of, but it turns out quantum mechanics has some phenomena that are very anti-relativity. They don't agree with relativity very well at all. So we have this growing clash with quantum theory from relativity. The Irishman I mentioned, John Bell, he proved a theorem, I should say. No local theory can account for the predictions of quantum theory. That's pretty bad when relativity, one of the mainsprings of 20th century thought, doesn't agree with the quantum theory. And so he published some things that were very important. They began testing them experimentally and found out, by George, he's right. There's something wrong when relativity doesn't agree with quantum processes. Then we have a thing which I'll skip over, the Lorentz gauge, that in order to solve Maxwell's equations for light, they have to assume that the vector potential, which is a function that tells about how the potential, when I speak of potential, I'm talking about the voltage that's in a wire, or the voltage that's in an electromagnetic wave. This voltage propagates outward according to certain rules, and they use this so-called gauge theory to help them solve the Maxwell equations. Well, in elementary particles, we had numerous problems with electrons. They're unstable as they're currently understood. The quark theory, same thing. You add up all the masses of the quarks that are supposed to be inside a proton, and it's 80 times too small. What's going on here? Why don't quarks add up to be the correct mass of a particle like the proton? If there's 3 quarks that make up a proton, why aren't the masses of the constituent quarks, when added up, equal to the mass of the proton? It doesn't work. All right, in general relativity and cosmology, that's the study of the evolution of the universe, more or less. We have a thing that Einstein said, and I want to just draw your attention briefly to this idea that Einstein had. Einstein said that if I have a passenger compartment, say propelled by a rocket, and here's a passenger in here, and then I have a man standing on the ground. Well, don't need to draw any compartment, who's subject to 1g, 1 times the acceleration due to gravity. Einstein said that if this man in a rocket is accelerating at 1g, that he cannot tell the difference between being in this chamber and standing out here on the surface of the Earth, for example, and being subject to 1g. So this is called the principle of equivalence. It was a very important idea that Einstein put forth. Well, I happen to have a lot of experience with rockets. And it turns out that when this rocket is fired, how does the force propagate into the passenger chamber containing the passenger? It propagates via low frequency sound and vibration, sometimes higher frequency sound and vibration. And every rocket that I have ever studied has really, really high levels of sound vibration. You can't get a 1G rocket by any current technology we know of to accelerate at 1G without this horrendous sound propagating through the structure into the passenger compartment that the individual is riding in. But gravity is quite different. Gravity is like a coherent effect that affects the entire body equally, and there's no need of propagating a force through it or vibration or sound. It just exists throughout a certain volume, and there's no sound associated with it. So Einstein's principle of equivalence, if he said that you cannot perform an experiment to determine the difference between these two, he would be wrong, because you invariably, even with the best rocket technology and the best sound insulation possible, you still have that sound that you can listen to. What about if you instead said it was an elevator with cables pulling this passenger compartment of the elevator room upward at 1g acceleration? Well, it turns out you can still detect the sound, because you can hear the natural frequency of the cables and how they vibrate or make noise. So the sound is a giveaway, and you can always tell the difference between these two. So I do not subscribe to Einstein's principle of equivalence, even though it proved to be a very valuable idea. Yeah, Roman.
Can I ask a question? What if there is no shell around the rocket? If there is only floor and the engine underneath, what then makes the person go up the acceleration of G? Just the floor.
That's right.
Then
But
there is no sound.
if you have some super futuristic propulsion system that doesn't make sound, I don't know of anything that doesn't make sound, and I once had an opportunity to apply for a job for an ion engine, which I never got the job, but those engines, they have a thrust of about 1/1000th of a Newton, a very, very tiny thrust. But I don't want to spend too much on Einstein's principle of equivalence, but I will say that it's not bulletproof, and there are some flaws in it, and they have caused problems, as we shall see. Another thing that happens is that in general relativity and cosmology, we have this no consensus on the behavior of accelerated charge. People have struggled with accelerated charge and have not come to grips with it. They have not been able to understand accelerated charge from first principles, let's say. We have a problem with the predominance of matter over antimatter. We'll talk about that in some detail later. We apparently have a surplus of positive charge in the universe. We look at cosmic rays, and about 99% of them are positively charged particles. So all these rays that are coming in from space are mostly charged particles with positive charge. And so we have also an accelerating or expanding universe. We can't really pursue all of these things in great detail, but I just wanted to bring them up, that there are issues. I've kind of talked a little bit earlier about the mathematical preliminaries, and I just pray you're not frightened by the presence of equations which may appear daunting at first. But ask any physicist what's the difference between matter and antimatter, or what is the difference between an electron and a positron. A positron being a positively charged electron, which is commonly called an anti-charge or an anti-electron. And how do these things both obey laws that we understand? Well, the answer you get to this question, if you get a decent answer, a coherent answer at all, is that anti-charge, such as the positron, obeys the same Maxwell rules as charge. It obeys Gauss's law, Ampere's law, Faraday's law, and so forth. But the details of how it's supposed to obey these things is missing. You won't find anything in the writings of Schwinger, Feynman, or the great discoverers of quantum electrodynamics. They don't understand why antimatter. Feynman and Dirac created an ad hoc theory. The assumed products or particles led to infinite results, as I discussed earlier. Paul Dirac discovered a remarkable equation that allowed us to understand how particles like electrons and protons have spin behavior. And he merged quantum theory in quite a remarkable manner. He merged the quantum theory with the relativity theory and created the so-called Dirac equation. And it was an outstanding achievement. But there are still a lot of problems with it, as I will discuss. None of these great men, Einstein, Dirac, Hawking, Schwinger, Wheeler, Bethe, Oppenheimer, or any others, ever provided a coherent understanding of antimatter and how it differs from matter, or what its conservation laws were for energy and momentum from a basic point of view. Now, many of you may have seen these Feynman diagrams from time to time. There was a very brilliant discovery or invention by Richard Feynman, but he shows in this example that a gamma ray can scatter off an electron and a positron will be created. So you have an electron and a positron created from a gamma ray, or in this case, two gamma ray photons involved. But notice something curious. The positron is shown scattering backwards in time. Time is here directed upward, but the positron is scattering backwards in time. So we had the time reversal going on here, and for a long time people thought, well, Feynman diagrams are just figurative or abstract depictions of what is going on. They're not real. But we found out that they proved to be so useful that it's hard to believe how they would not be real. But Julian Schwinger, who was a protagonist with Feynman, he said Feynman diagrams emphasize particles too much when we're dealing with fields. And so he took issue with them, but was largely ignored. The experts of the 20th century were largely silent on whether Maxwell equations have to be reformulated to describe antimatter, and what the laws of energy and momentum conservation were, for antimatter and how they differ from matter. And if there's a change, do the laws of thermodynamics differ for antimatter? If its time is reversed, we might not have an increase in entropy for aggregates of antimatter. Well, now here comes the equations. And if you want a break at any point, don't hesitate to ask for one. We ask, how does antimatter really obey Maxwell's equations? Maxwell's equations consist of basically, there's 1, 2, and these are 3 equations. So there's 2, and then 5, then 8. So there's 8 equations in Maxwell's equations that charge has to obey. And very briefly, whenever you see this symbol, divergence of a quantity, it means it's the source of something, whether it be heat, whether it be force, whether it be charge or whatever. In this case, you take the divergence of this quantity here and you obtain charge density. So it says surrounding charges there's an electric field, and that electric field determines the nature of the charge at the center of it. But with magnetic fields, they found out there are no magnetic charges. There's no such thing as a magnetic monopole. They've looked for them, never found them. Now this next equation is the basis for every generator and electric motor. And what happens is that when you change a magnetic field near a conductor of electricity, there is electricity induced, or an electric current induced, perpendicular to the changing magnetic field. That's what this means. So remember my little drawing of a tornado. The curl of this magnetic vector H says that whenever there's a current flowing in this direction, there is a magnetic field around it. So when you see this curl symbol, del cross something, or del cross E, del cross H, when you see that, you know that just think of a tornado. When the tornado is spinning, there's something pointing up, and that spinning is what we're concerned about in the Maxwell equations, the circulation, if you will. And so we ask, are positrons and their surrounding fields subject to the same familiar laws? And these are questions that no one ever answered in the 20th century. They did not understand it. Well, scientists have tried to simplify electromagnetism by introducing a thing called the four-vector potential. We're talking relativity now because everything in electromagnetism seems to abide by relativity quite nicely. The speed of light, the properties that are associated with these Maxwell equations, the Maxwell equations themselves are unchanged when we perform a Lorentz transformation, something that Roman once mentioned in an earlier lecture. So we have these four quantities, A0, A1, 2, and 3, which are what are called a first-rank tensor. Don't be flustered by that terminology. But using this one idea of a four vector, we can calculate both the three components of electric field and the three components of magnetic field using this basic procedure here, which is, I'll talk more about it later. So this is a very important idea, but notice the indices. Some of these indices are superscripted, and then we have others in physics that we'll talk about that are subscripted. And there's a difference, a physical difference in meaning between the way the indices of these tensors are written. So from the Feynman diagram, we know that all the anti-charge has to be reversed. That is, the time has to be, the charge has to be conjugated, so a negative charge becomes positive and vice versa. And the time has to be reversed according to the Feynman diagram. Well, when you look at the definition of an electric field, it's the gradient of this potential minus the time derivative of the magnetic vector potential. And so we plug in these minus signs. We're going to try to do electromagnetism for antimatter. We plug the minus sign in and we get a minus E there, but we also have to change the sign of the charge density because it's antimatter. The second Maxwell equation involving the magnetic field here is not changed because there is no charge involved, nor is there any time-like potential function involved. We have Faraday's law, the one that I said was important in motors and generators, electric generators, and in it both the signs of these two things are changed. And then in Ampere's law we have this is not changed, but the value of this displacement current is changed. So if you cancel out all of these minus signs, like here I multiply this equation by -1, it's the original Maxwell equation all over again. Same here, multiply it by a -1 and I get Maxwell's equation for Faraday's law all over again. Same here, I get minus a minus, which is Ampere's law with the displacement current. So we get the same Maxwell's equations again. We have anti-charge is quite remarkable. It obeys Maxwell's equations, somewhat modified though. Its arrow of time seems to be reversed to the one we're used to. Its electric field is opposite to that of regular charge. But there's another important thing that Dirac never quite correctly understood. The mass of a positron is not negative, as Dirac once supposed. We'll talk more about this later. We have already, as we look at the universe around us, we have this feeling like a person on yonder planet will be experiencing time at the same rate that I experience time here on Earth, or a person near a star may be experiencing it. And we have this notion of universal time, that it's proceeding forward at the same rate throughout the universe. Well, it turns out that idea is a myth. It's not happening the way you might intuitively believe it to be happening.
Time is not
constant times negative.
Yeah.
I remember. That's also.
We have, of course, in relativity, we have the so-called twin paradox, where a person traveling at a high percentage of the speed of light will experiencing time quite differently than one at rest with respect to the observer, or someone, for example, in a rocket going very fast will experience less time than someone's remaining on Earth, according to the twin paradox. So we have to, in order to understand time a little better, we have to understand tensor calculus. And it turns out that tensor calculus, as I mentioned earlier, Einstein was averse to it. He didn't like it at first when Minkowski taught it to him. But later on he learned to apply it with great skill, and he developed the theory of gravitation and general relativity. And so he began by understanding what is the distance between two events in space-time. And it turns out there are two different kinds of indices that are very important in this new relativity that Einstein was developing. One is called a covariant index, as this dx sub nu shows here, and then the other is a contravariant index, as in the dx super nu here. These are not powers of anything, but are indices. When an index is repeated, it means you sum over that index from 0 to 3. Well, we have associated tensors. That means I have the contravariant tensors with the indices above, and I have the covariant tensors with the indices below. The two are not the same, even though we may be able to express Maxwell's equations using both of them. And we mentioned this earlier, that I can express the components of the electric and magnetic field in terms of this 4-vector potential, and these are all contravariant indices. I apologize for the complicated terminology, but that's the way the math developed. But there's also a covariant form of the same type of thing, written in this manner, where all of the indices are down low. And this is not just fun and games with superscripts and subscripts. This is important physics that actually is in these indices, and whether they're raised or lowered indices. So we can express the Maxwell equations in a very concise form using these tensors. And this is what Einstein began to excel at as he began to write the equations of math, or equations of electromagnetism, in a tensor form. So we have the definition of the tensor here in terms of this so-called field tensor, F super mu nu. And then we have the Gauss's law and Ampere's law, which are implicit in this tensor equation. But it has a new tensor in it, and that tensor is G alpha beta. And guess what that refers to? Gravity. So that the laws of electromagnetism actually depend a little bit on gravity. There's a dependency here on the metric tensor, so-called G alpha beta rather. And these formula exhibit the tensor shorthand of physics. So it's very nice to be able to write these horrendous physics equations using this shorthand notation that they developed. But we also have the same laws for the covariant fields, and it turns out that these two are not equivalent. This equation is not the same as that other one that I showed you earlier, where all of the indices were superscripted. So what is the difference? Well, it turns out that if you know this tensor that determines gravity, you can move from one to the other, so that when you sum over the metric tensor, you can obtain a covariant field tensor from a contravariant field tensor in this manner. Well, one of the biggest oversights of the 20th century was something, and I discovered this over the course of several years. I want to draw your attention to these two ways of expressing Maxwell's equations in terms of contravariant equations and covariant equations. The two ways of expressing them are not equivalent. And it turns out that the charge density for matter is in the limit as gravity goes to 0 is just minus the charge density of antimatter. So the two, as we understood earlier, you conjugate the charge and you get antimatter from matter by just negating the charge density in this case. So this is the way, this is as it should be. But the zeroth component of every contravariant vector is minus its covariant counterpart with the time reversed. So covariant time is minus contravariant time. So antimatter is moving backward in our time, but forward in its time, which is covariant. In this, and again, the convention chosen here is purely arbitrary. There's nothing. You could have chosen contravariant as antimatter and covariant as matter, and it'd be perfectly legal. You just have to agree on the convention of what you call what, and that is the convention that I have chosen, is that covariant tensors in this formulation represent, in some cases, represent antimatter, and the contravariant ones that are the superscripted indices, they represent matter or charge. And the metric tensor from special relativity is there's a quantity called the proper time, d tau, and it's we can write this g mu nu as a somewhat different symbol, eta sub mu nu. Again, this is quite standard in this industry, where we use Greek indices for the four relativity indices, but Latin indices for just the three ones familiar from three-dimensional space. Well, so we have this thing called the Minkowski metric, which is essential in special relativity. I hasten to point out that this does not involve any gravitation or acceleration. When you use that metric tensor, there's no gravity involved. It's all inertial coordinates with no acceleration whatsoever. And again, we have this relationship that allows us to lower a contravariant index by summing over the metric tensor to obtain a covariant index. And so, as I mentioned earlier, contravariant time, covariant time, all the other three coordinates are the same when in Minkowski's metric. So within general relativity, we have a formalism to describe both matter or charge and antimatter or anti-charge. During the 20th century, this technique was right under our noses, but no one ever realized it. I never utilized this idea to understand antimatter and matter. And the proper understanding requires that we realize the physical significance of associated tensors. I'm talking about the covariant with the indices down low and the contravariant with the indices up. These are called associated tensors. And so nature admits both associated forms of field equations, as we showed earlier. No one ever caught on to this in the 20th century. They didn't realize they had the means to understand it, but they didn't put two and two together and make it work as it should. Well, this is an extraordinary idea that we have matter subject to these two types of equations. No one in the 20th century ever seemed to realize this. Well, so what do we have? We have a world, in the mathematical sense, we have two distinct types of every physical tensor. We have two types of coordinates, two types of metric tensor, two types of four-vector potential, two electromagnetic field tensors, which, as we saw earlier, describe the electric and magnetic fields. And we have two forms of each Maxwell equation, as shown there. We also have, as I mentioned earlier, a thing called gauge conditions, and I'm going to be discussing them when we approach the problem of wave-particle duality. We have a Lorentz gauge in this form and a Lorentz gauge in that form. We have also two so-called stress-energy momentum tensors. These describe energy and momentum, and there are conservation laws for them. The one for matter assumes this form, the one for antimatter that form. We also have conservation laws which tell us that when charge enters a closed volume as a current, the charge density in that closed volume must increase. When it exits a closed volume, when charge flows out of a closed volume, the charge density within that closed volume must decrease. So we have this equation for matter and its associated tensor form for antimatter. This is remarkable. I've never seen this in any book, and yet it dawned on me that this is the case. Okay. Yes.
So, is it correct that these tensor kind of equations and the mathematical forms are trying to explain how the antimatter can be explained? What kind of physical laws are behind the matter and antimatter? Is it so?
Yes, that's the idea.
In that case, is it do these equations explain the existence of, in addition to existence of antimatter, do they explain existence of anti-universe and anti-planets and or maybe anti-life? Can it exist in any way?
Well, we know that there are such things as anti-hydrogen. And when you take an antiproton and you orbit around it an anti-electron called a positron, you have a negatively charged nucleus and a positively charged electron, and that is anti-hydrogen. And we have created anti-hydrogen, and there have been a few other very light cases of antimatter that have been produced, but it's as far as large aggregates, we do not know that there are any anti-planets or stars or large bodies of that kind. It's as yet unknown. Marco.
And regarding this example that you just exposed, how long do they exist? This anti-hydrogen, for instance, how long do they exist?
They don't exist for very long unless you put them in a magnetic trap that keeps them from touching matter. Because as we all know, when matter and antimatter collide, they create enormous amounts of energy. And so if you can make antimatter insulated in a box where it doesn't touch anything that's made of matter, it can be kept for quite some time. All right. There's a symmetry between charge, I should say, not asymmetry in this case. There is symmetry between charge and anti-charge, as we saw earlier. And by all rights, we should see equal amounts of matter and antimatter around us, but we don't. For some unknown reason, charge dominates over anti-charge. Nobody seems to know why this is true. And like I say, if matter touches antimatter, it's very short-lived, and so it doesn't hang around long in the midst of gases that we're familiar with or in air. If you put it in a vacuum inside a magnetic penning trap, so-called, it'll stay there. Despite the resignation in physics that we don't understand why there isn't more antimatter, I believe there's a plausible solution, and that solution involves general relativity. Remember, we talked about those tensor equations, which could be one of two types. In 1916, there was a fellow by the name of Schwarzschild, and he was a field officer on the Russian front. He was a German captain in World War I. And he discovered that he could solve one of Einstein's field equations. I haven't mentioned any of them yet. And he found out that if you solve it, you obtain a metric tensor in terms of in terms of Newton's gravitational constant and the speed of light, c, and the mass of an object divided by the radius, so that this is the so-called Schwarzschild metric. Now notice if the radius were infinite, these ratios of 2gm divided by RC squared would all vanish, and this would just be that familiar Minkowski tensor of special relativity. It would simply be the familiar flat space garden variety special relativity that we learned about earlier. Well, when you measure the distance, shortest distance between two events separated by a small interval, we're talking about the distance between events in 4 space, that is, distance between events both spatially and in time. You encounter this concept here. It's called a geodesic. And it looks like this, that it's related, it has components of time and the radius, and in spherical polar coordinates it has the radius, the azimuth, and the the elevation angle and the azimuth angle phi. So the remarkable thing about what Schwarzschild discovered is that it allows us to calculate the ratio between anti-charge density and charge density. It turns out that this ratio of J sub 0 divided by J super 0 is simply the anti-charge density divided by charge density. And it's none other than the 0, 0 component of the metric tensor, which is just -1 plus 2gm over RC squared. Well, when the radius is equal to the Schwarzschild radius, that is RS equals 2gm over c squared, this quantity G0 goes to 0. So it turns out that on the surface of a black hole, there is no anti-charge present, according to this formulation. And the Schwarzschild metric is a diagonal tensor, and we know that you can find out what the anti-charge density is by multiplying it or summing over the covariant metric tensor in this manner. Well, this is remarkable. At the center of our own galaxy, there is a supermassive object known as Sagittarius A star. And over the past 2 or 3 decades, we have measured the motion of stars in orbit around Sagittarius A star. You can't see Sagittarius A star because all the light in it is redshifted completely because it's so massive. It's roughly 4.5 million times the mass of the sun. And we have on the surface of this A star, if you could see it, it's about 13 million kilometers in radius. We expect this ratio of antimatter to matter to be 0. No anti-charge on the surface of a black hole. Rather remarkable, since we've been struggling for a long, long time to wondering why we see so little antimatter around us. And we find that the dominant body in our galaxy, Sagittarius A star, happens to have this property that it sort of liquidates antimatter. You get the closer you get to Sagittarius A star, the less antimatter you will find, until at its very surface there will be no antimatter according to Schwarzschild's metric. But Sagittarius A star is quite far away from the Earth, 26,000 light years to the center of the galaxy. And it turns out that it really doesn't have a lot of influence on the abundance of antimatter here near the Earth or in our solar system. But everything in our solar system is under the greater influence of this black hole or this supermassive object. And we have about 200 to 400 billion stars in our Milky Way galaxy rotating around this supermassive object. So we're all more or less under the spell of Sagittarius A star, if you will. Okay, any gravitational field appears to have a diminishing effect on the abundance of anti-charge for the reason that the Schwarzschild metric describes what will happen in the vicinity of any mass m, as we showed earlier. There's a table I want to show you real quickly, and then we'll discuss a little bit about it. Here's the mass of Sagittarius A star, about 4.5 million times that of the Sun. Its Schwarzschild metric, radius rather, is about 13 million kilometers, about what, a fifth of the distance between the center of the Sun and Mercury. So it's not all that big, but it's still bigger than any planet or star that we know of in our immediate area. But the deficit of antimatter, as seen on the Earth, due to Sagittarius A star, is about 5 parts in 10 to the 11th. So it's not a very big effect from Sagittarius A star. It isn't a profound thing out at this distance from the center of the galaxy. But at the surface of that object, as I mentioned earlier, the ratio of those two should be 0, according to theory. On the Sun, if the Sun were compressed to about a little under 3 kilometers in radius, it would be a black hole. If you could compress all of the mass of the Sun into an object with about 6 kilometers in diameter, it would be a supermassive object and exhibit the properties of a black hole, according to Schwarzschild's theory. Well, if we look at the this quantity G00, which tells us what the product is between matter and antimatter, it turns out that it's deficient by about 4 parts in a million on the surface of the Sun, and so on. The planets are pretty insignificant in their effect on antimatter, even on their surfaces, because they're not very massive compared to the supermassive giants like Sagittarius. We know that every galaxy that's been observed apparently seems to have a supermassive object at its center, or a black hole, if you will. Our nearest star, Alpha Centauri, is not much different than the Sun. If it were compressed to within 2.7 kilometers, it would be a black hole. But the effect of all of these masses on the abundance of antimatter is slight. It's not very much. But wherever antimatter might emerge, it runs into gravity. And so we find that these things are all going to take a toll on the abundance of antimatter, according to theory. Okay. Now, let's move on away from that antimatter discussion for a moment. Paul Dirac said, I have to have negative masses for positrons. In fact, he said his equation predicted them. Well, there are some things that happen in modern physics, a thing called vacuum polarization, in which a gamma ray comes along, or rather a photon is moving along, and it is supposed to, this is a virtual process. No one ever sees this happen. It becomes a positron and an electron, which then mutually annihilate, and the photon proceeds on its merry way. However, this does not, this process is known to occur only in a non-virtual way for very high energy gamma rays, and not for just any photon. And what scientists began saying after Dirac and Feynman is that we're seeing creation of matter almost out of nothing, because they said, I've got a negative mass and a positive mass, and the two add up to zero, and therefore I can have creations of mass and matter and antimatter ad nauseum. I can continue to create a universe out of nothing, virtually, with this process. And of course, you look at the writings of Stephen Hawking in Great Britain, and he seems to parrot the same idea, that we're looking at a universe that is created virtually, creation out of nothing. Well, we know that that's not quite true. There's 4 serious problems with the Dirac theory. Dirac says that there are negative mass electrons and negative mass positrons. I mean, he says that the 2 of them are possible. He says that there's vacuum polarization that creates a kind of a free-for-all where you can keep having these photons create particles, and those particles themselves can emit photons which themselves undergo vacuum polarization, and so you can have one generation or nested vacuum polarization after another, and it becomes very complicated and almost mind-boggling. And this is what physics of elementary particles has boiled down to in the 20th century and even in our century, is that we're looking at multiple sequences of vacuum polarizations and virtual processes, and about anything is possible with it, because they've stretched the rules to the point where virtual particles and virtual processes can occur almost ad nauseum. They've created a free-for-all for these virtual processes. And then Dirac said, well, I believe that there's a sea of virtual particles that are negative masses, and the reason we don't see them is because they're unobservable. Well, that's kind of hard to buy. I think it strains credulity. He assumed the existence of this sea of virtual particles occupying negative energy states, and you don't see them because he, by design, made them unobservable. But the reason he did that is because he knows that in physics, something at a high energy tends to decay, and like atoms, when you have an excited hydrogen atom, it will decay and an electron will go down to a lower energy state. So by the same reasoning, if you have negative masses in states somewhere, then all of the positive masses should decay or fall down to negative energy states, and this is why we can't allow that to happen. That would be almost a disaster. So he omitted the possibility of negative masses being observed in this theory that he developed. So we have this unsubstantiated confusion created by Dirac's sea of negative mass particles. Well, it turns out that if you follow this associated tensor formalism that I showed you earlier, all that goes away. But let's look at Newton's gravitation law here. It says that the force between two masses is proportional to the product of the masses divided by the square of the radius between them. And that's Newton's law of gravitation, verified and known to be true on countless examples of astronomy. But if one mass is positive and the other is negative, guess what? It would imply that there would be gravitational repulsion. And we never see any evidence for gravitational repulsion. Gravity is a hard thing to measure for elementary particles, but as yet there's no evidence for gravitational repulsion. What's more, this tensor I told you about that describes the energy of a particle is called, I don't know how that got in there. That should be equal. I'll get rid of it later. That should be an equal sign. All of the energy of the electromagnetic field surrounding a positron is positive because it's the sum of the square of these two items, the electric field and the magnetic field. You don't get negative masses by adding up positive quantities. So it turns out that if you take the mixed divergence of the covariant stress energy momentum tensor, you obtain this formula. And it turns out that that is none other than the familiar, and this should have been, I don't know how it got in there, it shouldn't be there. The force density is a very familiar thing from Lorenz's force law, where you multiply the charge density times the electric field, and that tells you how much force is pushing away or attracting, depending on the signs. And then a magnetic field is created by the presence of a current. So, Dirac's sea of unobservable virtual negative mass particles becomes completely unnecessary. Antimatter is subject to the laws of gravitation. Antiparticles have gravitational attraction for all particles, matter or antimatter. not gravitational repulsion. And moreover, we know that this process called vacuum polarization can only occur for an electron and a positron when the gamma ray has a large amount of energy. So we don't really need some of Paul Dirac's assumptions to do physics right in the 21st century. One of the greatest discoveries of the 20th century was that distant galaxies are moving away from us at a very high speed. The more distant they are, the faster they're going away. This gave rise to the so-called Big Bang theory, because if the universe is finite and it's expanding, then it must have begun at some point in the past. And the only problem is there's a number of other things that are going on. I mentioned that 99% of the radiation coming in from space in the form of cosmic rays is positively charged. It's either protons or about 9% of it is helium ions, which are also positively charged, but much more massive than hydrogen ions. And less than 1% of the radiation coming in is electrons. And the question here is, what happened to all of the negative charge in the universe? If the universe is supposed to be electrically neutral, why are we seeing all of this positive charge coming in and impinging on the Earth in the form of cosmic rays? There appears to be a surplus of positive charge in our universe. From all appearances, this is the case. Well, a universe with even a slight surplus of positive charge will expand due to Coulomb repulsion. Two like charges together repel, and if galaxy A and galaxy B are charged with the same sign of charge, they'll push away from each other. Same with any positively charged masses. And so we end up with, I'll rush through this, but you can actually calculate the pressure caused by this repulsive effect. And the Gibbs law that I showed earlier here gives gravitational attraction for nearby masses, but Coulomb electrical repulsion for more distant masses. I'm sorry, this is under the assumption that we have electrically positive charge distributed throughout the universe. And we look at interstellar gas and we see a lot of it just happens to be protons, or some of it is neutral hydrogen, but a lot of it is just protons out in intergalactic space. And we find that this positively charged matter is causing our universe to expand at quite a bit. This is my supposition based on the observed abundance of positive charge in cosmic rays. There's a pattern thought to obey Hubble's law. Edwin Hubble developed this thing where he said the velocity of recession or receding velocity of a galaxy is proportional to its distance away. And so this constant h is Hubble's constant. And right now it's almost 74 kilometers per second per megaparsec of distance away. And a megaparsec is 3 times 10 to the 19th kilometers. So it's a huge distance, but these very distant galaxies, you have to use new units because, kilometers and meters are just too puny to measure the vast distances. And so they use megaparsecs. Well, Hubble's constant has fluctuated quite a bit over the past 80 years or so, between 50 and 90. And it only gives positive values for velocities. The universe would be dominated by 2 opposing forces: local gravitation attraction with gravitational collapse of supermassive accretions of gas and stars, creating galaxies and black holes at the center, plus surplus positive charge. But there's also this ubiquitous, that means present everywhere, mutual Coulomb repulsion between positively charged parts, creating large-scale expansion. Viewed in this light, the universe appears to be a machine that transforms hydrogen and its ions into more massive elements while generating surplus positive charge. It leads to an ever-expanding universe consisting of galaxies. We have 2 options from all of this. The current theory in vogue says the universe is finite. Everything began 13.7 billion years ago from a point called the Big Bang, and this is called the Big Bang explosion. But there's another possibility. I think it's a very real possibility that's been is not understood or perhaps is ignored. It's not inconceivable that the universe is infinite and that the formation of this positive charge surplus in any closed volume will lead to large-scale expansion. Okay, in conclusion, I want you to look at this. This is the extreme deep field photography of the Hubble Space Telescope. It didn't actually photograph it. This had to be processed by computer in a very meticulous manner over, I think, 1 million seconds of exposure while the Hubble telescope was orbiting around the Earth. It was focusing off at a distance at this particular area, and it took a lot of computer processing to produce this picture. But look at it. As far as the eye can see, there are galaxies, galaxies, and more galaxies. This is supposed to be at 13.2 billion light years distant. This is what these scientists would say is right out near the vanguard, near the very vanguard of the expanding universe. But as I see it, what we have is throughout the field of the visual field of view, we see nothing but galaxies. And the more we magnify the picture, all we see is more and more and more galaxies. There's no end to it. So we see little evidence of any end to the galaxies. Isn't this a marvelous thing, that what we've done in the 20th century, and have been able to see these pictures of the galaxy, of the universe 13.2 billion light years away? To me, it's astounding.
And there was also some sort of theory that explained that in 500 billion years, the scientists who will be living on Earth, they will not see the stars. So they don't have this option to see the stars. We are the only ones who will be able to see them. Because the universe is expanding and the stars will be farther and farther away.
we'll talk about that more later. But thank you for your attention. I'm sorry this was so technical and long.